In this video, we'll cover the problem number of closed islands. We'll be given a 2D grid that consists of zeros, which represent land right here, and then ones, which represent water. An island is a group of connected pieces of land, so a group of zeros that are connected. And these connections are just up, down, left, right. And a closed island is an island, so again, a chunk of land, that is totally surrounded by water, which is represented by ones. So if we look in this example, this island right here, everything around it, using our up, down, left, right directions, is a 1. It's surrounded by water. So it's a closed island. But something like this, these 3 zeros, they are an island, but they're not entirely surrounded by water. This way, they are surrounded by water, but this way you go out of bounds. And so that's not a closed island. So we have to count the number of closed islands in this problem. So in this problem, we have an implicit graph, and so we can explicitly write this out. So we have our implicit graph. Our nodes are cells in the graph, or positions in the grid. Or sorry, our nodes are cells in the grid, or these kind of like each location here is a node in our grid. Edges / neighbors are basically cells or position. Cells is correct. Cells that are up, down, left, right from a given cell. So for example, this 0 right here is a node, and its 4 neighbors are this 1, this 0, this 1, and this 1. If we're on this node, this 0 in the top right corner, it has only 2 neighbors, this 1 to its left, and the 0 that is down from it, because it could go right and up, but those are both out of bounds. So we have an implicit graph here, and we can only focus on the pieces of land, because really that's what we're counting, right? We're counting closed islands, and in order for it to be an island, it must have land. So our graph kind of has a bunch of nodes that are connected to each other. Actually, the graph could have both water and land, but that doesn't actually matter too much for the algorithm here. And in this graph, as we know, number of islands is basically asking us to count the number of connected components in the graph. For this problem, we're being asked to count the number of special connected components. So we are counting connected components, but they must also meet some special criteria. In this problem, the special criteria is that the island, the connected component, must be closed. So the question is, how can we determine if an island is closed? Well, if we have some cell that is an island cell, a land cell, which means it's a component of an island, and we go in our 4 directions, there are 3 options for what we could see. Option number 1 is what we saw here. We go out of bounds. Option number 2 is we see water, as in a 1. And option number 3 is that we see a 0, which is land. Absolutely nothing else can happen. And so we can talk about what happens in each of these 3 cases. If we go to one direction and we see more land, then, we're just continuing the island. So we don't need to do anything special. If we go out of bounds, like we saw here, then it must not be a closed island. Because if we have a land cell that is directly touching, or like kind of next to the border, as in like right here, the 0 cell is on the border's right here, meaning if you go upwards to the right, you go out of bounds. If that is the case, then we know the entire island that this 0 is a part of is not a closed island. And how do we know if we have a closed island? Well, if for every 0 going in all 4 directions, we either get a 1 or just more of the island, for every single 0 in the island, if that is true, then we know that we have a closed island. So we're going to handle this the way we handle typical connected components counting problems. We are going to try from every node. So for each node in our graph, meaning we're going to iterate over every row and every column, if the current cell is unvisited, we are going to figure out if it is a closed island. If it is, we're going to increment our counter. Otherwise, we're just going to kind of note that it's visited and move on. In terms of how we figure out that a particular 0 is a part of a closed island. So this 0, when we hit it, we are going to use a breadth first search to kind of traverse its entire component. So we're going to go in these directions. And what we'll do is basically we're trying to figure out, is there any zero who is going out of bounds if we go in our forward direction? And so what we'll do is we'll say, all right, for each zero, we're going to check adjacent cells, so go up, down, left, right. If we have a 1, that's fine. We don't need to add it to our queue, but it's not causing any problems. That's what we expect for a closed island. However, if we ever go out of bounds, so if we're on a 0 cell, a land cell, and then we check our 4 adjacent directions, and one of them, or at least one of them, goes out of bounds, then immediately we know the entire island that we are currently exploring is not closed, and we should not update our counter. So that's the conceptual idea. It's pretty similar to number of islands with this additional check that we actually need to validate that we cannot go out of bounds from a land cell. So we can go ahead and start coding this now. So we'll grab our number of rows, grid.length. We'll have our number of columns, grid0.length. We'll have a visited set, which we need to keep. And this needs to persist in between our BFS traversals. So we're creating it globally instead of making it within the BFS function itself. Because if we're at the 0, we kind of mark the whole island as visited, then we're iterating over our loop, we hit this 0, we don't need to explore the island again, we should know that it's already visited. Other than that, we need to know the number of closed islands, which is going to initialize, or we will initialize it to be 0, and then we'll make sure to return it in the end. Now, we're going to iterate through our grid. So we'll say, have our row go through everything from 0 to num rows. Our columns will do the same thing. Col plus plus. Now here, as always, we're going to skip anything that we've already seen. So let's do cur position string. And we'll write a function for this, because we're going to do this multiple times. We'll do get position string of row and col. This is going to be a pretty simple function. We can just write it right now. Just going to take in a row and a column, and it's going to return this string. So it's going to be, the row, and then a comma, and then the column, just so we have a unique identifier for each position that we can use in our visit set. So if we've already visited our current position, we can just go ahead and continue. No need to do anything. Then we can say, we can check if it's a closed island. So if it is, or we'll have a function here, check if is closed island. And that'll take in, let's see, we'll need the grid, we'll need our current position, and we'll need our visited set. I believe that should be everything. Okay, and if we have a closed island, we're going to increment our counter. If it's not a closed island, we don't need to do anything. And we're assuming that our check if is closed island method or function is already going to make the visited updates that we need to make. So we can come up here and we can, or we'll do it below this function. We can start to write this function. And I'm realizing there's actually one thing we forgot. So before we do, one more thing we should check. If we're at water, we don't need to even be checking if we have a closed island, right? We only want to check it when we have land. So we'll say, if grid at row at col is not equal to land, we'll define a constant for what land is in a second. But in this case, we can also continue because we don't need to be trying to explore an island if it's not even land. And up here, we'll define land as a constant, which is 0. Okay, great. Now we can work on this check if is closed island function. So it takes the grid, the start row, and the start col, and then the visited set. And here's where we're going to write our BFS. So we're going to create a new queue. We are going to add the start row and start col to our queue. And we are going to mark this position as visited. So we'll say get position string, start row, start col. And you can see already here, having that function is nice. It's making sure that we don't have to make the string ourselves. And if we want to change the format of the string, it's easy. We just do it in one place. Okay, now we'll iterate as long as our queue size is greater than 0. We'll have our 3 steps. We'll remove a node, we'll process the node, we'll add neighbors. Now, when we remove the node, we can say row and col is equal to queue.dequeue. We can use our destructuring here. The process node will come back to it as usual. Now, here, I'm going to have a function that gets neighbors for us. So we'll say get neighbors. and that's going to take the grid. Actually, no, it's just going to take the row and the call. Let's do this. Actually, these are not necessarily neighbors, because we're just going to go in all 4 directions in this function here. But sometimes that we might go out of bounds, and that's actually not a neighbor in the true graph. Because if there's a position that's out of bounds, that is just nothing in our graph. So I'm going to name this adjacent positions. And we'll name this get adjacent positions. And we should define our directions array before we write that function. So this is just going to give us the changes we need to go in all directions. And there we go. Okay, and now we can write our function here, which gets the adjacent positions, takes some row and call. We'll create an array adjacent positions that we can return in the end. And then we'll just simply say for each of our directions, direction of directions, we will destructure our row change and call change. We'll say new row is going to be row plus row change. And we'll say call or new call is call plus call change. So now we have our new positions, and we can add each of these to our adjacent positions array. So we'll push new row, new call right here. Is there a typo? Okay, no. All right, so now we have all of our adjacent positions. Now what we can do is we'll iterate over each of them. So we'll say for const adjacent position of adjacent positions. Now we'll have the neighbor, or like, I was going to call this neighbor row and neighbor call, but that's not actually the case because, like we discussed, some of these are not really neighbors. So we can say on adjacent position row. Yeah, I guess we can just do adjacent position row, adjacent position call. It's going to equal the adjacent position. And we could be doing our destructuring right here in these loops. That's up to you, personal preference. I prefer to have this here and then destructure afterwards in these cases, but that's up to your choice. Now, we have to check a few things here. We have to make sure, the first thing is if we're going out of bounds, we know that this is not a closed island. If we have a 1, that means everything is fine, we just keep doing what we're doing. So if we have water, we just keep going. And then the last case is if we've already visited something, we don't need to visit again. So if we visited, continue, like keep going. Or like move on, skip this one. Okay. So I'm going to write an isInBounds function for us, just because I don't want too much logic in this function here. So this is going to take the grid, the row, and the call. I'm going to grab the num rows and num calls again. And unfortunately, we are copy and pasting the code. I've not been able to think of a great way around that for this specific case where we want like the number of rows and columns. But it's not the end of the world. So we'll check if the row's in bounds. So if the row is greater than 0 and less than num rows, and then the call in bounds, we'll do the same thing. So call greater than or equal to 0, and call less than num calls. And we'll return whether or not both of these are true. Okay. So here we can say if not is in bounds, and then we'll pass in our adjacent position row and our adjacent position column. And if it's not in bounds, you might be tempted here to just return false and say, okay, this is not a closed island. You know, over here we receive that false value. We say it's not closed, and we just don't increment our counter. We do nothing, and we move on. However, one thing you have to be careful with is you can imagine when we are on this 0. So we're kind of iterating through this row. We hit this 0. Immediately we go up. We say, hey, that's out of bounds, and we return false. However, in that scenario, then this 0 has never been marked as visited because we immediately returned false on this 0 when we went up. So we're not going to return false immediately. We're just going to mark in a Boolean variable that, hey, this is not a closed island, but keep doing our exploration so that we mark everything in this island as visited. So we actually need a Boolean that we're going to be returning. So we'll say let is closed island equal true. Here, what we're going to say is, oh, we found something that can go out of bounds. It has an adjacent position that is out of bounds, and it is land. We're only going to be adding things to our queue that are land. So we know that the current position is land, which means this adjacent position that is out of bounds is next to land. So then here we want to say, all right, like this is not a closed island. So we'll say is closed island equals false, and then continue. We don't need to we don't need to do anything else with this position because obviously this is an invalid position. It is out of bounds. But we do need to make sure that we note that we do not have a closed island here. Other than that, we can say if the adjacent position is water, we don't need to do anything. Or really if it's like exists and is non-land. So we can say if grid at the adjacent position row and the adjacent position column is not equal to land, just continue. We don't need to do anything. Remember that the ordering is important here. If you put this check before the is in bounds check, then sometimes you'll have something that's out of bounds, and then this right here will cause problems. So make sure you're careful with the ordering when you're doing this problem, or these sorts of problems. Right? Lastly, we can say if visited already has, I'll just write it right here. Get position string, the adjacent row, adjacent call. Then we can also continue. We don't need to visit it if we've already visited it. And so we can delete these. Other than this, now we know that we have something that is a neighbor. It is inbounds, it is land, and it is unvisited. So we want to continue exploring. We want to look at it, see if it has anything that's out of bounds, and mark it as visited. So what we're going to do is we're going to mark it as visited and say, hey, we're adding this to the queue. So to any other positions in the future, don't add this to the queue. Actually, we'll need our get position string here. Yeah, so in the future, whenever anybody is trying to add this position to the queue, immediately they will be stopped and they will recognize that it is already visited. So that's why we're immediately adding to the visited set. And then we're also going to add this position to our queue here. So we can just grab this array, actually. All right, so we're adding the row and the call. Now, we kind of have the skeleton of this function mostly done. One thing to note is we want to be returning this boolean in the end. And so you can notice we're defaulting to true. Like we assume that the island is closed until we find evidence that it is not closed. Meaning until we find a land cell who is like, when you go 4 directions from that land cell, you go out of bounds. But the default here is true. Okay. Now, the other question we want to answer is, what do we want to do in the process node step? Well, the process node step answers the question of what work do we want to do for each node. We could be doing things like adding it to the visited set or checking if it is out of bounds, but we're doing all that here in the add neighbor step. So really, the way we've written the code, no work needs to be done in the process node step for this problem in particular. Okay, I believe conceptually we have covered most of the pieces for this problem. We can go ahead and run it and see if there's something I missed. Okay, row change, call change, we're missing initializer. Oh, it looks like I just didn't finish that line of code. Here we need to set this equal to direction so that we can destructure from something. Grid at 0.length. Cannot read properties of undefined. Oh, looks like I'm probably not passing in the grid when I call is in bounds, which would make sense. Here's the grid. Yeah, and the way I knew that was happening is because it was saying, grid at 0.length. So grid at 0 is undefined, and it was trying to do undefined.length. But I know, obviously, the grid is a grid. It shouldn't be undefined. And so if it was breaking, that means we're not passing this argument here, and so it's receiving it as undefined. Okay. And now that we've added grid here, that should not be an issue. Okay, it passes this case, and if we submit, see, all right, looks like it passes there as well. All right, well, that's all for this video, and thank you for watching.